Hey y'all, welcome back. It's the start of semester two. We need to do a little bit of work. I found in the past that students have some misconceptions, algebraic misconceptions that will be important to us. The topic of the next chapter in geometry will be similarity, and we'll find that certain kinds of equations arise in the context of similarity, in particular quadratic equations. So that's what we'll discuss. But I'll build up to that. And what I want to talk about today are square roots. I suspect that you don't really get some of this, or you have misconceptions about it. So let's go back to the start here. So first of all, of course, we need a definition of a square root. Notice the a here. I'll talk about the square root in just a moment. A square root of a real number n is a real r such that r squared equals n. So for instance, the square root of 9 is 3, because when you square 3, you get 9. That is 3 squared is equal to 9. But 9 also has a second square root, which is negative 3, because negative 3 squared is also 9. And in general, um, reals that have square roots have two of them. This is certainly true for all positives. Now, there is one case I'll ask you about on the worksheet of a certain real that has precisely one square root, but for positives anyway, there are two square roots. And those, of course, differ only in sign. Now, let's talk about the so-called principal square root. I don't know if this language has ever been used with you, but it is standard language here. The principal square root of a real n is that non-negative real p such that p squared is equal to n. So for instance, though 25 does have two square roots, notably, and that is 5 and negative 5, 25 only has one principal square root. And that principal square root is 5, because 5 is not non-negative and 5 squared is equal to 25. And in general, every non-negative real has a unique principal square root. We do have a symbol for the principal square root. That's what you see up at the top. That strange symbol that wraps around the n. That's often called just simply the radical. And that's read as the square root of n. And almost always when you hear someone say the square root of n, they mean the principal square root of n, which means the positive root. So for instance, as you see, the square root, that is radical 49, is simply 7. Now, here's something we know about the two square roots of n. They differ only in sign, like for instance, our example of 9. It had two square roots. They were 3 and negative 3. And those differ only in sign. But we also know that radical n is the positive square root of n. So it must follow that the two roots of any positive n are the square root of n and the negative of the square root of n. So for instance, the two roots of 81 are the square root of 81, that is the principal square root of 81, which is equal to 9, and the negative of the principal square root of 81, which is equal to negative 9. Now, we're about to have to solve some equations here. And to do that, we'll need the concept of absolute value. Now, I'm sure you've seen this before, but I did want to go over it again. I offer a two-part definition of square root, of absolute value. And what we do here is we break our cases up into those where our input value to the absolute value function is either 0 or positive, and cases where that input value is negative. So if n is 0 or positive, the absolute value of n is simply n. If, on the other hand, n is negative, the absolute value of n is negative n. And I'm sure you're familiar with the usual way that we symbolize absolute value. It's n with the straight bars, the vertical bars on either side, as you see. Just a few examples. The absolute value of 3 is 3. 3 was positive, so nothing changes. However, the absolute value of negative 7 is 7, because negative 7 was, of course, negative, and the absolute value is then the negative of that, and the negative of negative 7 is positive 7. And finally, the absolute value of 0 is simply 0. Now, let's look at a few absolute value equations. So we'll start with the simplest variety. So we have the equation, the absolute value of x is equal to 12. Really not much work is to be done here. All we have to do is think of the definition of absolute value and ask ourselves what the values of x could be such that its absolute value is 12. And of course, the two possible values here are x equals 12 and x equals negative 12. The absolute value of 12 is 12, and the absolute value of negative 12 is also 12, and those are our two possible solutions. Let's do one that's just a bit more complex. Here we have the absolute value of 2x minus 3 is equal to 15. Let us solve that. And we should expect that we'll get two solutions to this. So how does this begin? Well, to say that the absolute value of some quantity is equal to 15 means that that quantity can either be 15 or negative 15. So here's where we began. We have two possibilities, that 2x minus 3 is equal to 15, or 2x minus 3 is equal to negative 15. And this is the general procedure. Whatever you find inside of the absolute value symbol, say that it can equal what's on the right or equal the negative of what's on the right, and then we solve both of these out. So I'll do the first. On the left-hand side, we would add a 3 to both sides, and then we would end up with 2x is equal to 18, which means after we divide by 2 that x can equal 9. Now for the second of the two equations, once again, we'd add a 3 to both sides. And in this case, we find that 2x equals negative 12, which means that another possibility here is that x can equal negative 6. So either of those two values will make absolute value 2x minus 2x minus 3 equal to 15 true. Now, let's talk about the square root of n squared. This will be the context. This will be the kind of expression that we'll see in the work that we do with similarity, and we'll find that this turns into an absolute value equation. So here's what you'll be tempted to say. This is one of the misconceptions that I referred to at the start. You'll be tempted to say that the square root of, and again, when I say the square root, I mean the principal square root, you'll be tempted to say that the square root of n squared is simply n. This is false. In general, it is false quite specifically when n is negative. For instance, the square root of negative 5 squared is not equal to negative 5. It cannot possibly be equal to negative 5 because that radical symbol always returns the principal square root, which is non-negative. Instead, think of it like this. The square root of negative 5 squared is, of course, the same as the square root of 25, because negative 5 squared is 25, and then the square root of 25 is 5. So the square root of n squared is not in general equal to n. When n is negative, that's simply not true. So what instead do we say about the square root of n squared? It's not equal to n. Instead, it's equal to the absolute value of n. And why is this? This is true because the square root of n squared, that is the principal square root of n squared, must be positive no matter the initial value of n. And absolute value does precisely that work for us. It does always deliver the positive. So let's solve some simple equations here, and let's make sure that we can do it properly. We should be able to do it properly now. So let's say that we have the very simple equation that x squared is equal to 121. Now, I expect that you know the answer immediately to this, but you might, if I had asked you to show your work, you might have done it incorrectly. So let's make sure that we can do this correctly. So start with the equation x squared is equal to 121. We initially take the square root of both sides, so we get the square root of x squared is equal to the square root of 121. Now, as for the left side, that is the square root of x squared, that's not just x, that's the absolute value of x. And the right-hand side, that is the square root of 121, which, as we know, is the principal square root of 121, is 11. So what we get then is that the absolute value of x is equal to 11. And we know that this has two solutions. X can equal either positive 11 or negative 11. And that's where we find ourselves at the end. Now, here's the mistake that students make. And this would be the right time in your mathematical career never to make this mistake again. Students will often say, well, the square root of x squared is equal to x, and the absolute value of, the square root of 121 is plus or minus 11. And then they'll say that the solution is x equals plus or minus 11. Well, the final answer is correct, but the way they got there is not correct. The square root of x squared is not in general equal to x because the radical symbolizes the principal root, which must be positive. And we know to say that the square root of x squared is the absolute value of x, and we know to say that the square root of 121 is not either plus or minus 11, but rather is just simply 11. All right. Now, later on, we actually have 4 sections of algebraic review to do, and this is the first. We will need certain properties of the square root relation, one in particular, which is often called the product property of radicals. And what it says is this, it says that the square root of x times y is equal to the square root of x times the square root of y. And I wanted to step through the proof of this with you. On the worksheet, you'll prove that the square root of x divided by y is the square root of x divided by the square root of y. And the procedure that you will follow there is precisely what I will do here. Okay, so how do we prove that the square root of x times y is the square root of x times the square root of y? Well, we must think of our definitions. We know that the radical represents the principal square root. And then how would we establish that root x times root y is the principal square root of x times y? Well, that's two parts. We must first of all prove that it's non-negative because principal square roots must be non-negative. And we must also prove that the square of the right-hand side, that is square root of x times square root of y, is equal to what's under the radical on the left-hand side. Okay, that will tell us that it's a root, and then if it's non-negative, it will be the principal square root. So first of all, how do we know that the square root of x times the square root of y is non-negative? Well, both of those involve the radical, so both of those are the principal square root, and we know that then both of those are non-negative. And of course, we know, just basic algebra, that the product of two non-negatives is itself a non-negative. So the right-hand side, square root of x times square root of y, is non-negative. It cannot be negative. So now let us prove that the square of the right-hand side is what is contained under the radical on the left. Okay, then how will we do that? Well, before we hop into this, do note that the square root of x times the square root of x is equal to x. And why is that the case? Well, that's just simply the definition of root. The square root of x is a root of x. And what is the root of x? It's what you multiply by itself to get x. So it just has to follow that the square root of x times the square root of x is equal to x. Okay, so let us then square that right-hand side. So you see it there, the square root of x times the square root of y squared. Well, what does it mean to square? It means to multiply a quantity by itself. So this becomes square root of x times square root of y times square root of x times square root of y. And then this is all multiplication, and we know that multiplication is associative. That means that we can do it in any order that we please. So let us rearrange and now call it square root of x times square root of x times square root of y times square root of y. And then think about that. Okay, so we have root x times root x. That is simply by definition x, and then we have root y times root y, which simply is by definition y, and so we find that we get xy. So yes, uh, root x times root y is a root of the square root of x times y, and moreover, it must be positive, so it is the principal square root. And just to hop back a second, it then follows that the square root of xy is the square root of x times the square root of y. Now, finally, here's a misconception that students have, and it gets them into no end of trouble when they believe that this is true. Let us disprove that the square root of x plus y is equal to the square root of x plus the square root of y. Now, you might find it somehow intuitive that this is true. Well, all I have to say to you is that it is not, and we can prove so by counterexample. So the way that radicals interact with addition is very different than the way that they interact with multiplication. Okay, so what's my counterexample? I say let x equal to 9 and y equal to 16. And I say that in this case, the left-hand side, the square root of x plus y, is not equal to the right-hand side, that is the square root of x plus the square root of y. Before I show this, do note what the left and the right say and how they ask us to perform operations in a different order. On the left-hand side, we are asked to first perform addition and then take the square root of the result. On the right-hand side, however, we are asked to first take square roots and then add the results. So the order of the operations is different. On the left-hand side, it's addition and then take the square root. On the right-hand side, it's take the square root first and then perform addition. Okay, so let's look at the left when we substitute in 9 and 16. So we do the addition first, which is what the left-hand side tells us to do. So we end up with the square root of 25, and we know, of course, that that is 5. Now let's do the right-hand side. That is the square root of 9 plus the square root of 16. Well, on the right-hand side, we take the roots first. And so the square root of 9 becomes 3, and the square root of 16 becomes 4. And then, second operation, we add, and we get 3 plus 4 is equal to 7. But I believe that you will agree with me when I say that 5 is not equal to 7, and then it follows, of course, that we have our counterexample. So in general, it just simply is not true that the square root of x, the square root of x plus y is equal to the square root of x plus the square root of y. Okay, so that's the first part of our algebraic review. Next time we'll come and we'll actually do a little bit of work that builds on this.